So my name is Matthew Beckley. I'm a data scientist with OpenTopography, and today I'm going to be talking about an introduction to digital elevation models. This is the third webinar in our series. Next couple of weeks, we have some more seminars coming up at the same time, same day. So be sure to check those out. So as I mentioned, this is the third webinar. All of the webinars will be recorded. So if you can't make the live webinar, you can always go to our YouTube channel to check out OpenTopography and view the webinars at your leisure. Just a little bit of logistics. It'll be similar to previous webinars if you've attended those. Only the presenter and moderators will be able to speak. So if you do have any questions, please put them in the Q&A section of Zoom. We have people online that will be answering questions during the webinar, but we will also reserve time at the end for questions, or if their question is kind of complicated, you could always ask it at the end of the seminar. So just a rough agenda, we're going to talk about some raster basics. Then we're going to talk about the different interpolation methods. Then we're going to focus on the OpenTopography specific gridding methods that are available to users. We'll talk about OpenTopography raster products. And then at the end, I'm going to do a little bit of a longer demo to sort of walk through some of those raster products that are available through OpenTopography, what some of the different settings are, and then we'll also talk about API access. So I want to get started off with some terminology because there's a lot of confusing terms out there and sometimes terms are misused. Most people have heard of DEMs, digital elevation models. This is a generic term. And very often it's used to mean digital terrain model, which is the second term there in the list. A digital terrain model is also referred to as a bare earth model. And what that is if you look at the figure on the ground at the bottom right here, those blue points are, say, LiDAR points from an airborne LiDAR collection. And when you create a digital terrain model, you're basically creating that red line. You're taking all the points that are on the ground and ignoring the points above that, points that hit an automobile, within the trees, on buildings. One thing to note is that you could see here, in this case, the digital terrain model actually went underneath that building to make a continuous surface. Depending on how people process the data and create those digital terrain models, sometimes there'll be no data there, or sometimes they will extrapolate the surface out. Depends on how it's been processed. The second most common term you probably see is a DSM, digital surface model. That's often referred to as a highest hit model because with LiDAR, it's taking the sort of highest hit. With structure from motion or any kind of model that's created from imagery, it's creating a DSM by default because, as you can imagine, when you're taking imagery, you're seeing the tops of everything. You're not penetrating into the trees. So if you look at the figure in the upper right, this is the same figure except creating a DSM from that data. So in that case, they're taking the top return from the LiDAR collection and creating a surface of the top of the data that was collected. Another thing to note here is that you can see in this building, there might have been only a LiDAR point on one side of the roof and another, and it gets cut off. So sometimes you can see some weird artifacts with buildings. So just be aware of that. It depends on the density of the data that was collected. The next two terms are sort of synonyms, and you may see them used interchangeably, but basically they are the same thing. So you have a normalized DSM, which is an NDSM as an acronym, or you see the acronym CHM, canopy height model. Both of these things are basically just a difference of the DSM and the DTM. So you subtract the DTM from the DSM to get a difference. The reason you'll see it referred to as canopy height model is because in forestry applications, that differencing is basically giving you a proxy of elevation height of the trees. So it's giving you tree height essentially. But as you can imagine, if you're doing an urban study where there aren't a lot of trees, this is kind of a misnomer to use in an urban environment. So a lot of times for urban studies, you'll see it referred to as NDSM. It's doing that same thing, it's doing a difference, but in an urbanized environment, you're getting things like building heights or, heights of electrical wires, things like that. So it's just the same term, just depending on the scientific application, you'll see it used differently. The last one I want to talk about is called an REM. It's kind of a newer one. It's not as popular. It stands for relative elevation model. And basically it's used in hydrology. I have a slide later in the talk that goes into a little more detail, but basically it's removing the slope of a river from the elevation profile, so that you're left with just localized elevation change. And so you can see interesting things about river dynamics with those models. So I'm going to talk about, again, rasters. Now, for this talk, since it's about topography, obviously rasters are going to refer to a digital elevation model, but a raster is basically a grid of squares or pixels where each pixel has a value. Obviously, you can have rasters for non-topography elements like population density or rainfall intensity, things like that. But for the purpose of this talk, when I refer to rasters, I'm referring to digital elevation models. So these set of grids are basically forming a continuous surface where Z is estimated at each of one of those points. And another point about terminology that could be confusing is you might see rasters referred to, or digital elevation models referred to as 2.5 dimensions instead of 3D, and not truly 3D. And this was a little confusing to me at first, but basically what this means is that a raster is representing a single layer, so with an elevation at each pixel. So things like trees or overhangs or caves, a raster won't represent the top and underneath of that overhang and then the ground below that. It represents one of those things. A true 3D format is more like the point cloud, which we talked about last week, where you have XYZ points in a cloud. And so you can go into a cave and do a scan of that cave or that overhang, and you'll get a true 3D sort of representation of that topography. So if you ever see that 2.5D, that's kind of what it's referring to. Grid resolution or raster resolution in this case is sort of the width of each of those pixels. Most people are familiar with this. Most data sets that we have in OpenTopography tend to be 1 meter pixels, but we do have some finer resolution. And then just as an example, this is a sort of representation of a digital elevation model. On the right, as most people could probably predict, this is sort of a pyramid. So you can see this center value is 400, let's say it's meters. Then you have 350 around that, 300 around that, all the way down to 0. So if you were to contour this digital elevation model, it would look like a pyramid, because basically that's what it is. It's a digital representation of a pyramid. So ultimately, the point of a raster is we're trying to get from these sort of irregularly spaced sampled points. In this case, we'll talk about, say, an airborne LiDAR collection, where you have these points in yellow. Each point is XYZ, but it's not sort of regularly spaced. So we're creating a sort of regularly spaced grid. It's a continuous surface, but you need to sort of assign a value to each one of those cells. So this is where interpolation methods come in. There are a variety of interpolation methods. Nearest neighbor is probably the one method where you're not interpolating or doing any averaging, but we'll talk about that in the next slide. But ultimately, these gridded products are easier to work with. They're faster. They create better visualizations in general. So like here's an example of a digital terrain model that was created over the meteor crater in Arizona. So I'm just going to go through some of the interpolation methods that are common. I've highlighted the top 3 in bold because those are the interpolation methods available to OpenTopography users if you use our portal. But there are a ton of different interpolation methods out there. Each one has its pros and cons depending on your scientific objective. The first one most people probably heard of is a TIN, which stands for a triangulated irregular network. Next one is an inverse distance weighting, followed by local gridding, and all those are available to OpenTopography users. But then you might commonly see natural neighbor, nearest neighbor, krigging, and splines. I'll talk about natural and nearest neighbors in the next slide. Krigging is a really nice technique. It's one of the few sort of interpolation techniques that is also very good at extrapolating out. So it predicts your trends for the interpolation bit, but then it can actually extrapolate out where you don't have data, and it does a pretty decent job at that. The other nice thing about kriging is most kriging applications that you'll see in commercial software also comes with an associated error map. So if you see some irregularities in your kriging interpolated surface, you can pull in that error map and see there might happen to be high errors during that interpolation. And splines, there are many different splines, and I just wanted to make one point that could be useful to users is there's many different splines. Some of the splines you have to be careful in that they don't preserve your actual measurement. They're fitting a surface to that entire set of points, a sort of best estimate. And so with some splines, you might go to a sample point where you have a measurement, and if you sample your DEM or your interpolated surface, it won't match your measurement. So you have to be careful. Like I said, there's lots of different splines, but some of them do have that property. So you want to be careful with that. So now I'm just going to talk about the difference between natural neighbor, nearest neighbor, and inverse distance weighted. So I'll talk about natural neighbor first, since that's the most complicated. But basically in a natural neighbor, you're weighting your interpolated point by area. And how you're doing that is you're first creating a set of Voronoi cells or Thiessen polygons. I'll refer to them as Thiessen polygons because that's how I was sort of taught when I was in school. And a Thiessen polygon is essentially creating a polygon around each point. Sometimes they're called a seed. And to the effect that each point in that plane is closer to your seed point than any other data point. So it's sort of a measure of the influence of that point on the data set as a whole. And so with a natural neighbor, what you do is you go ahead and you create these Thiessen polygons for all your data points. And then let's say you want to do an interpolated data point. And so in this example, it's that black dot in the center. With natural neighbor, you would create a Thiessen polygon for that interpolated point that you want a value for, and then you intersect that polygon with the other Thiessen polygons. And what you get is then for each one of those data points, you weight it based on the amount of intersecting area. So as you can see in this figure here, each one of these points is an elevation point, say, and the green area is sort of showing how much area is intersecting your interpolated point. So you can see this polygon here has the largest area intersecting with the purple area, and so that is going to get a larger weighting. And so basically you would go through and take each of these elevation points and weight it by its proportion of area that intersects your Thiessen polygon and apply that to that value. Inverse distance weighting is doing a similar thing, except instead of weighting by area, it's calculating a distance to each one of these points and weighting by linear distance. So it's the same technique, but instead of area, it's using linear distance. And then finally, nearest neighbor, which is sort of the simplest and really isn't doing any interpolation, is it takes the closest point by distance and assigns that point to your interpolated value. So it's not doing any averaging or weighting or anything. So people that want to preserve sort of the raw data or a little worried about interpolation or averaging methods will use nearest neighbor. You do have to be careful if it is a data set that is kind of sparse in some areas. Nearest neighbor could be applying an elevation that's very far away to your point, and that could lead to some weird effects. So it depends on the sort of data collection, your density of data, which method would be appropriate for you. So TINs, or triangulated irregular networks, most people are probably pretty familiar with these. These are a vector sort of format of a surface, basically creating a surface from the points by connecting neighboring points with these triangles using a Delaney triangulation method. These triangles are created such that if you created a circle around the 3 points in your triangle, there'd be no vertices within that circle. So here's sort of a representation of that concept on the right. The other thing with TINs is if you've ever done them manually, basically you want to avoid the temptation to create these long sliver triangles, because that's not very representative of what most surfaces are, unless it's like a cliff face or something like that. So that's TINs. And so, as I mentioned, tins are one of the products that OpenTopography provides. I should mention they're sort of a pseudo tin, and I'll talk about that here. We use the Last Tools program to create our tins. That was a program created by Martin Eisenberg. So let's say you start off with your irregular LiDAR points. With Last Tools, it creates a tin from those LiDAR points, and that's sort of a temporary tin. And then a grid gets overlaid on that tin. And then at each one of the grid cells, the tin is sampled, and that is what is output by OpenTopography. The reason that is because as much as tins are great and they're really useful, some software has problems with it. CAD software tends to work well with it, but some of the other GIS softwares, it's easier to work with a regular grid. So in a way, this is what we call sort of a pseudo tin. It's sort of sampling that tin at regular intervals. The next gridding method that's available to OpenTopography users is called local gridding. And what local gridding is let's say you have a set of irregularly spaced points that's LiDAR points here and that are represented in black dots. You lay a grid on that, you can control that grid cell size, and then for each grid cell center, you apply sort of a search radius. And so I'm just going to animate that. You can see the little pop-up in the lower right there. And that search radius will intersect a certain number of points, and then you can run some statistics on those points and apply that value. You can also control the size of that search radius. So let's say it's in an area of sparse data and you want more data points to be average, you can increase that radius, and you can see here it selects more data points to be averaged, and then you run some statistics, and then you apply that value, and then that value will get applied for that grid cell. And then you proceed through each of the grid cells and perform that operation. One feature that's nice with local gridding is because you might have sparse data, and if you choose too small of a cell size, you can do null filling. And I'll talk about that in the demo, but basically you can do an averaging of surrounding points to fill in those nulls if you have kind of a sparse data set. So now I'm just going to walk through some of the products that you can get out of the local gridding. This is sort of an base image of the Kaibab Peninsula. This is the Kaibab Plateau, I should say, in the North Grand Canyon. So it's a mix of sort of flat topography, forestry, and then some steep cliff sides. And so the first product that you can get is a tin, which we talked about. But then if you use local gridding, you can also get a mean, inverse distance weighted, and you'd expect those all to be somewhat similar because it's just they're all doing different averaging. But what's interesting to me is here's running the min value on that local gridding. And I wanted to just point this out because it's really interesting. As you can see from the first couple of plots I did, this isn't a filtered data set. So I took the full data set, and then I said, take the minimum value. And so what this is doing is taking the last return. It's giving you basically a ground classification. If you really wanted to do a true ground classification, you would go back, filter this data set for just ground points, and then take the minimum. And then you would really have a really nice ground classification of your data set. You could also get the max. So that's taking out the top value, the maximum value in every cell. And then there's a couple metrics that you can get. So you can get point count. So this is basically point density. I just wanted to point this slide out because so this is an airborne LiDAR collect. And as I mentioned in the last webinar, when you're trying to do these collects, a lot of times there's the LiDAR is sweeping back and forth. So you get a LiDAR swath, but you want to overlap those swaths just to make sure you have good ground control and that you don't have any data gaps. Sometimes you might have more or less overlap, and that's what you're kind of seeing in these swaths here. You're seeing a sort of difference in overlap of data from swath to swath. And then you can also do standard deviation. And this plot should make sense since we had the vegetation in the data set. You're seeing a ton of standard deviation around that plateau where there's all the forest because you're getting elevation values from the tops of trees, the ground, mid of trees. So your standard deviation is going to be very high in this case. So this slide's really important, and I'll hammer this home in the demo as well. I want to take some time with this slide because it's a really a point that people are confused with using OpenTopography. And there's two main methods that you can get raster data from OpenTopography. You can either dynamically grid the point cloud from scratch, which is what we have on the left here, or we have pre-computed rasters that our data providers will give us, and you can utilize those. So I'm just going to talk about those two things and the pros and cons between them. So with every data set, I will start with the dynamically gridded point cloud. If you have the LiDAR data, you can run a gridding algorithm on it. Depending on what classifications are available, you can create a DTM or a DSM. One of the downsides of doing this method is that because you're starting from scratch, you're limited to the amount of points you can select, and it's going to be much slower because you're gridding directly from the raw point cloud. So that's a little bit of a downside. On the plus side, you have a lot more control and customization of the grid that you're creating. So you can control that cell size. If the data is a very dense data set, you might want to do a 50 centimeter grid or something like that. You also can control the null filling. If you do a smaller grid, you can sort of fill in areas where there's no data. And with both cases, there's visualization and custom output formats available, but I'll talk about that in the demo. By contrast, on the right, there's the pre-computed rasters. And as I mentioned, these are rasters that the data providers give to us. They've already gridded the data, so they might give us the point cloud and some pre-computed rasters. The downside of that is you're sort of beholden to whatever the provider gave us. So a lot of times that's DTMs, DSMs, but sometimes it could also be intensity. From some of the forestry community, we'll get canopy height models or canopy density. So we could get other products. The real positive or benefit of using pre-computed rasters is if you don't really need the point cloud and the customization, you can run much larger jobs and they will run much faster. And so you can really get a large DEM much quicker using this method. Again, there's less customization. You can subsample that DEM, but you can't sort of resample it. And obviously, as I talked about, there's visualizations and custom outputs formats available for those raster products. And we'll go through this in a little more detail in the demo to show you what I mean. So at OpenTopography, we have a pretty wide user base. It's pretty amazing. We obviously have people that are interested in topography and want bare earth terrain models, but we have people from the forestry community, we have gamers, people from the hydrology community. And so everyone sort of is after something different. And so we don't want to limit our users. So we try to make as many products available as possible. And for the forest community, this canopy height model is one product that they're very often interested in. As I mentioned, the canopy height model is that difference between the DSM and the DTM to get sort of a proxy of canopy height, height of the trees. But there are many other products that the forestry community is interested in. They have canopy density, canopy cover, base canopy height, biomass estimations. One of our data sets, the one I mentioned over the Kaibab Plateau, they provided canopy density and some other forest metrics. So that's a really cool data set if you're interested in forestry. And just to tie this into what we talked about last week with the point clouds, the waveform LiDAR is really useful for forestry applications. Waveform LiDAR is, if you missed last week, is basically instead of getting just a single return from the top of the tree and maybe the middle and the bottom, the waveform is basically a distribution of that entire energy of that LiDAR pulse and how it interacts with the canopy. And so you can get better estimates of biomass because you're not just getting a single point, you're getting the entire distribution of that energy as it intersects the canopy. And one of our recent products that I'll talk about at the end, the JEDI, is based on a waveform LiDAR and actually is producing a canopy height model near global resolution. So again, this is a canopy height model. And again, just to keep with the nomenclature, it might see it as an NDSM, a normalized digital surface model. In this case, it's a canopy height model over Lookout Mountain in Oregon. And I just wanted to mention, obviously, if in case it wasn't obvious, in order to create the canopy height model or NDSM, you need both the DTM and the DSM, and it's simply doing a raster math difference of those two. The accuracy of it will depend on the classification. Obviously, if you have more data and you have accurate sort of tree heights or ground locations, you're going to get better results for your canopy height model. And so we talked about the grading methods. So for those two types of grading methods available to OT, you have the TINs and the local grading. But then you could take those DEMs and sort of do further visualization in both cases. So we had an intern last summer who did a really great job of sort of revamping our raster visualizations. And so now you have all of these different types of visualization options available to you. You can do hillshades, a color relief. You could do a colorized hillshade, which is basically draping that color relief on the hillshade with transparency on the color. And that's what you see in this image here of Mount St. Helens in Washington. That's a colorized hillshade. But you also have slope, aspect, roughness, and you can also do Google Earth outputs for any of those visualizations. So next I want to talk about sort of rasters for different use, basically using rasters for QA, QC. So as I mentioned, one of the products from the local gridding is a point count, or essentially a point density. For every cell in your raster, it's counting the number of raw points that intersected and assigning that count. And this can be really useful for QA, QC. So in this example here, this is another airborne LiDAR collect. And people were looking at this and saw these sort of strange vertical lines where there was a lot of point density, and we're wondering what that was. Went back to the data collector, and what happened was the aircraft actually sort of hit some headwinds and sort of slowed down. And so as you can recall, a lot of these lasers are sweeping back and forth. And so when the plane slows down, it's sweeping back and forth over that small area. And so you're collecting a lot more data in that one section. So anyway, things like this are really useful for also looking a little deeper into the data to understand what's going on. Another interesting example of how rasters can be used for QA/QC is actually was published in this paper. In this paper, they detail how people initially thought they had found a new fault scarp, and that's indicated by these black arrows here. And you might be hard to see, but there's a line sort of here that's highlighted with these V's. And they gridded the data, and then what they saw is, it might also be difficult to see, but there's some corduroy effects, what they call corduroy effects. And basically what they found was this wasn't a new fall scarp. It was just an artifact of the gridding and the LiDAR collect. So as we talked about earlier with the point counts, when data is collected with an airborne platform, a lot of times there's swaths, and those swaths get overlapped. But if those swaths aren't properly georeferenced, there can be slight differences in the height of those two. And so what when you group those together and hillshade them, you'll see this sort of alternating pattern, often referred to as a corduroy effect. And when you see that, you know you're probably at the edge of each swath. And as we talked about last week, sometimes there's a lot of errors in those edges of swaths. And so you want to be careful about how much you read. You don't want to read too much into anything you see if it's on the edge of a swath, particularly if you're getting corduroy effects. So now we're going to talk about REM, which is a relative elevation model. As I mentioned earlier, so briefly, a relative elevation model is basically when you have the river profile and you're removing that slope effect from the profile. So here is a diagram on the right that sort of explains this. The blue line is sort of the topographic profile of the river, and you're taking the slope along certain sections and removing that slope. And then what you're left with is sort of the local sort of elevation changes of that river. So it's often referred to as detrending the river. And this is really kind of useful because it sort of highlights some river morphology, sort of the history of the river and where it was flowing before. It could also help model sort of future sediment transport, and also makes really nice visualizations. So our intern last year did a really great job of coming up with a Python package to create these sort of graphics that you see here on the bottom using RiverRem. So if you go to our GitHub page, OpenTopography, the package is called RiverRem, and you could play around with it. It's very easy to install, and you can make some really great visualizations of REMs. So I'm just going to talk a little bit more about some different terminology that you'll see in the hydrology field. Two sort of confusing terms that you'll hear often are hydro-flattened DEMs versus hydrologically enforced DEMs. So on the left here, we have a DEM that was created using the tinning algorithm. And what's highlighted there in the red boxes is a water body right here. And then there's a river that flows around that. This could be like a holding pond or something. And as we talked about last week, water with LiDAR can be really tricky depending on your collection. Very often the LiDAR pulse gets either absorbed or it gets deflected like a mirror, and so you don't get a return. And so a lot of times over water bodies, you'll have no data. And then when you go to tin that data set, you'll get these triangulation artifacts. This is from the tinning algorithm because a tin is creating, remember, a network between all the data points. So it might have to go very far to connect to the next data point. And so that's what you see here. And so what a hydro-flattened DEM is, it gets processed, it goes through and takes the adjacent elevation and applies that to the water body. And so what you see here is, then you'll see that just a flat elevation applied so that you don't get those tinning artifacts. And so it's a purely cartographic enhancement, but the USGS, as part of their LiDAR base spec, the DEMs that they're putting out will have this hydro-flattened applied, and you can get those data sets through OpenTopography. A hydrologically enforced DEM is much more advanced and much more useful for analysis. It's more than a purely cartographic element. What a hydrologically enforced DEM will do is it'll go through and sort of modify the DEM such that water flows as it would in reality. So in this case, you have a highway system and it has some culverts. And so the DEM is actually modified so that when you run a hydrologic analysis like ArcHydro or Tau DEM on this, water from up in the headwaters will flow down and it will flow through those culverts, as opposed to if you didn't have this, it would hit that road and might flow differently and it wouldn't represent reality. So this is a really useful analysis tool for hydrologic and hydraulic modeling. Many people use it for sort of anything from landslide predictions, or Department of Transportation could use it for maybe where to put more culverts in if they model this and they see that one culvert is getting overloaded. You could also predict where there might be undercutting of roads. So it's a process intensive to create these, but it's really useful from an analytical perspective. So I think this is my last slide before we go into the demo. I'm going to talk about global rasters because these are really popular with a lot of users, especially international users. We have about a dozen or so different global rasters. They are each collected with different sensors. Some of them are radar based, some of them are LiDAR based, some of them have bathymetry. And they vary in resolution. In general, most of them are about 30 meters, but most of them cover most of the globe. And I just wanted to highlight a couple of our more recent additions. So that's the top 3 entries are in bold. As I mentioned, we have, As I mentioned, we have the USGS 3-depth rasters. They come in a variety of resolutions. We have a 1 meter, 10 meter, and 30 meter. Those are all DTMs, digital terrain models. So they've had, they don't include vegetation. And as I mentioned in the previous slide, these are hydro-flattened. They've been corrected. The water has been corrected. You shouldn't see any kind of tinning artifacts. As I mentioned, when I talked about the canopy height model, we have the JEDI data set. It's a very coarse data set. This is the level 3 gridded product. So its resolution is about 1 kilometer. But the unique thing about this data set, what makes it interesting, is you have near global canopy height model for, like I said, near global, which is really useful for forestry applications. It's also a digital terrain model because it's based on a waveform LiDAR, and so it's much easier to get an accurate ground return that way. It is it's nearly global. The JEDI instrument was on the International Space Station, so you're limited by the space station's spatial coverage, which is about 52 north to 52 south. But it's still pretty good. The last one I want to mention is our continental European DTM. This was created by the group at OpenGeoHub and Open Data Science. They did a really cool project where they created a digital terrain model using machine learning. And so they basically applied JEDI and ISAT-2 LiDAR to get ground surfaces and apply that to existing DSM models. So they used a hybrid model that had European DSM, Raster, and other things. And they applied this machine learning technique to strip out trees and buildings and create a digital terrain model at the scale of all of Europe. And so that one is at 30 meters. It's a newer data set that we've released and is a really interesting one. The others have been in there for a while. Most people are probably familiar with them. They're a mix of DSMs and DTMs, mostly at 30-meter resolution. And my final point on the global rasters, and we'll talk about this in the demo, is one of the real benefits of these is almost all these, except for the USGS, are available with an API. So if you don't want to use the web portal, you can sort of script access to these and sort of go and dynamically grab a data set in your processing workflow and not have to go to the website at all. So it's a really nice way of grabbing data. So I'll come back to this slide in case people need access to our information. But for right now, I'm going to jump into our OpenTopography website, which hopefully most people are familiar with. And I'll just really quickly run through some data access. I did this last week, so it might be a repeat, but just in case people are not familiar, there's 2 main ways of finding data within OpenTopography. You can use the Find Data Map or the data catalog. So most people are probably familiar with this. You can select a region and it'll sort of break down what intersected your area of interest. One other thing I want to mention is for global data sets, you can reset the map here. If you want to see the extent of global data, you can click on that drop down and it'll show you the spatial extent of one of the global rasters. As I mentioned, JEDI is limited to 52 north and south, but we do have data sets like Copernicus that are pretty much near global. They have data even in northern Greenland, Antarctica. So that's just a way of sort of seeing the spatial coverage if you're ever interested in that. Going back, if you select an area of interest, and you might, especially in California, we have a lot of data sets. You'll see a ton of data sets that intersect that area of interest, and they're broken down by tab, sort of a high resolution, a LiDAR, 3DEP, and NOAA, which we don't host, we actually dynamically access through Amazon. And then community contributors, users that who have uploaded data to our servers, and then the global and regional DEMs, which I talked about on the last slide. One other thing I want to point out, when you get it in a section where there's a lot of data, it's really confusing to see. You could always select this pin here. So like, let's say you want to inspect this data set. If you select that pin, it'll show you just that data set. So you can see sort of the spatial extent of that particular data set. So let's go to that data set, and then we'll show sort of some of the gridding techniques that are available to you. So again, you have your point cloud data, which you can grid from, or your pre-computed raster DEMs, which you can grab from. So first we'll go through gridding directly from the point cloud. So you just select an area. And the first two options are your sort of point cloud variables that you can filter for. You can filter by classification or change your output format. We talked about that last week. But I want to focus on these next couple of customizations. So 3A and 3B are your gridding options. How are you creating that digital terrain model, digital surface model, etc. The first one is the tinning algorithm. And so again, you can control your output resolution. You can also control the size of your triangles. So as I mentioned, tin is really nice if you want to have data everywhere, because it'll try and connect all of your data points with a triangle. But there might be cases where your data is really sparse and you don't want to do that because it's going to be misleading or it's going to show really misleading data. You can control the length, the maximum length of a triangle. So let's say you anything over 20 meters, you don't want to have a triangle, you just put in 20 meters to do that. You can output in GeoTIFF, Esri arc grids, or ERDAS Imagine outputs. GeoTIFF is always generally the default. It has really good compression. So I would recommend just sticking with GeoTIFF. Most software can read and access GeoTIFFs. Your next gridding option is what we talked about, was the local gridding. This is the option where you can specify that search radius. You can also control your output resolution. And these are the variables where you can run statistics on for each grid cell. So you can do the min, max, mean, inverse distance weighted, standard deviation, and point count or point density. If your radius value is too small or the data set is quite sparse, you can always go through and do null filling. And so what null filling is doing is it's doing what's called a roving window. That window has a preset. It could be 3 cells by 3 cells, 5 by 5, or 7 by 7. And so it'll move along each grid vertex. And if there's no value and you want to fill it, it will do an inverse distance weighting of all the points within that 3 by 3 or 7 by 7 cell, and then assign it to your missing missing data. So it's a nice way of filling in those missing data pieces. And so then once those are your two gridding methods to create your digital elevation models, but then you may want to visualize those models. And so these are your options to do that. You can, as you click on each one of the visualization types, it'll give you the options available to each type. So for a simple hillshade, you can change the vertical exaggeration. You can change the lighting source. You can do a multi-directional, which is kind of a cool feature where it's actually lighting from all different directions. So you get sort of a different looking hillshade. It's can be really useful. Color relief and color hillshade, we have some predefined color maps that you can use. And then, as I mentioned, slope, aspect, and roughness. You can output in a variety of formats. And for each one of these, you can output a Google Earth KMZ. Next week, we'll be talking about 3D point cloud visualization. So I won't talk about that here, but if you created a digital elevation model, you can also create vector contours and output the visualization. You can control the contour interval. You can also output in a couple different formats, Esri shapefile, DXFs, which are popular in CAD, and GeoPackage. And so that is if you were dynamically gridding from the point cloud. But as I mentioned, a lot of our data providers will also give us precomputed rasters. So in this case, we got the data from the US Forest Service, and they had given us rasters that were already created. So they created a DTM, DSM, and they also created intensity raster. So with this, like I mentioned, it'd be really useful because you can really select a larger area, you're not as limited, and your job will run much faster. So if you really need to grab a lot of data and you don't need the customization, just go with the pre-computed rasters. You have the same visualization options, so I won't go through that. But if you select both DSM and DTM, you'll see here now you're able to get the option to create a canopy height model. And that canopy height model is just the simple raster math difference between the DSM and the DTM, You can resample the canopy height model to a finer resolution if you want to, but it really wouldn't make sense. You'd probably stick with the resolution of the input grids. And then you can also output Google Earth files of those canopy height models. So that's that. Other thing I wanted to mention, excuse me, I have to move my bar, is I wanted to show you one of the sort of completed jobs from the local gridding, because it can be a little confusing for users. Sometimes you get a lot of images. And so for each gridding method, if you choose a tin and local gridding and then you visualize it, you're going to get visualizations for each one of those products. So here's an example of that job I ran over Kaibab Peninsula or plateau. And you could see for the tin, it's creating a hillshade, a slope, aspect, roughness. There's a KMZ for each one of those. And then for each of the local gridding products that I select, it's creating a visualization. So for the min, the max, etc. And so just be aware of, like, you could end up getting a lot of grids and a lot of data sets, depending on if you select visualization and you select both gridding methods, you'll get a lot of data. And so the last thing I want to talk about is sort of API access. This is a really sort of popular piece of OpenTopography. A lot of people sort of code up access and they don't want to go through the portal. So to get more information about our API, you go to from our homepage or where you see this menu, you go to Resources and Developers API. And then you can click on this either REST API or this link, and it'll take us to the Swagger Open API spec. And you'll see this type of interface, and you just click on Global DEM, and then select Try It Out if you're not familiar with it. So when you click Try It Out, it gives you some information about these are all the data sets that are available through the API. You can select any one you want. We don't have the USGS available. That may be happening in the future, but we're not sure right now. And then you can edit sort of your bounding box is in Latin lawn, and you can specify your output. You'll put in your your API key here, which I'll talk about as I run this, and then you hit execute, and it'll run from within this interface because you're trying it out. But while that's running, I'm going to show you how you can get your own API key. So a couple of different ways. One of the easiest ways is right from the main page. If you have your account, you just select request an API key. Otherwise, you can do it from your My OpenTopo dashboard. And so you go down to the bottom under My Account, you'll see a link called My OpenTopo Authorizations and API Key. And if you click on that, you'll see this button, Request API Key. If you don't have an API key, when you click that, you'll be assigned one. If you've already created an API key, when you click this, your API key will be stored there. You're not getting an API key each time. You get one API key, and it'll be stored there so that you can use whenever you want. So going back to the Swagger docs, you can, if you want to just play around and get familiar with the interface, you can use that, put in your own API key there. But you can see I hit execute, and I can actually download that file here if I want, or it gives you sort of the syntax of how to use it from a command line or from an HTTP request. So here, if you were running it from command line, you can use this curl command, and it shows you the sort of syntax of how you put in the different variables to grab that. Obviously, you put in your own API key. Or if you're doing it from within a browser and you want to do an HTTP request, here is sort of the syntax of how to grab that data using that. So it's a really nice way of if you want to script, if you're more comfortable with programming and you want to dynamically grab data, you can grab most of the global data sets through the OpenTopography API. And so I'm going to stop it there, and we'll look at any questions we have. Looks like most of them have been answered.
Yeah, thanks, Matt. That was great. We've got 10 minutes or 9 minutes, I guess. We've been answering questions in the QA. Emily and I have been trying to keep up and do our best, so you should definitely look there. If there are other questions, feel free to toss them in the QA and we'll go through them.
Okay. Yeah, it looks like Emily posted one to answer live. The question is, can you recommend some resources, books, classes, blogs, etc., for more education about interpolation? That's a good question. I don't have any. I mean, we have a lot of education materials. I don't know if we have any specifically about different interpolation methods. And yeah, I'm a blank on any specifics. I'll have to think about that. Yeah,
there's a lot of good resources out there. I oftentimes just ask Google, right? Like,
yeah, maybe ask ChatGPT can give you an answer to that.
Yeah, I mean, like things like, yeah, there's like tons of resources out there. Esri has things on sort of geospatial methods. Yeah, there's a lot. I don't have a great single source.
And definitely, I mean, or just sometimes I just read the documentation for like whatever software package I'm using. They'll have a pretty good summary of the different interpolation methods, and it can vary, and it can vary your results quite a bit. So you have to be a little careful depending on. Some people just want interpolation for a pretty picture, in which case you don't really care that much. But if you're doing any kind of scientific analysis, the different methods can produce different results. So you have to be a little careful what you use.
The other thing I just noticed that, OpenTopo there's a lot of options on OpenTopography, but the idea is that we're doing the computations for you. And so it's sort of designed to encourage you to explore these different methods and how they represent the data and which method is perhaps best suited to your application. So, use the interface and run some test jobs and create those browse images and look at the data set and think about, is a local gridding minimum the appropriate choice for what I want to do versus a triangulated, approach, or that iterative exploration is a powerful part of OpenTopography, and at least to test things out. And you can do these over small sample sets. You don't necessarily have to process your whole data set initially. You could start with just a couple test jobs, explore the space, and be like, okay, what I really need is an inverse distance weighted local grid. That's the best choice. And so I'm going to use that.
Yeah, it's definitely a great recommendation. And I do that a lot of times too. Like I'll just select everything on a small area and sort of see what it looks like and do some initial exploration that way. It's really, OpenTopography is great for doing that.
Matt, there's an open one. Do you want to answer this one about compression and file formats?
Yeah, are there Python modules you want for for processing tar files? I don't know if I've ever. I mean, there's LastPy is a really useful program, Python package for working with LiDAR data. I don't know if how it reads tar files directly. Usually I use just like the OS or the sys sort of module. I think those might be able to read tar files directly, but I don't know that 100%, but I would recommend, I think the OS module, you can do quite a bit, just cracking open a tar file.
And for the API in particular, the API does not return a compressed file. It returns a TIFF, a GeoTIFF natively.
I believe so. I don't know if we've implemented, we might have implemented compression. If it was, I don't think it is. I think Chris is right. I don't think we are.
Yeah.
With some of our other outputs, we are. And in that case, we're using the LZW compression algorithm, which is pretty good. There was another question.
The output. So the output is basically a cloud optimized GeoTIFF. So it's got some kind of baked in compression in it, but it's not a bundled tar GZ or something that you need to crack open before you can use it. You're just getting a file that you should be able to read directly as a GeoTIFF.
On the API, you mean?
Yeah.
Yeah.
Any possibility of utilizing OT computational power for external data sets currently not in OpenTopography? This is a tricky one. We've been, and I'll answer this if you don't mind, Matt. We've been working on trying to get more data into OpenTopography. But to pull data from another source into OT to process and apply our algorithms that that data is sort of not already linked into the system is not something that is straightforward. A lot of the systems inside of OpenTopography are built on open source tools. So if you have data and you want to sort of recreate an OpenTopography like process, you can send us an email and we can help point you towards sort of how to implement some of those algorithms. Some of them are available via our GitHub. Things like the local gridding algorithm, we wrote it a long time ago. It's actually now baked into the PDAL open source package. And so if you want to do sort of large scale local gridding types of processing on a data set that's not inside of OpenTopography, we can make some recommendations on how to build a PDAL pipeline that would call that writers.gdal is the bit of code inside of PDAL. Yeah, so this is like definitely one that you should send us an email. we can talk more about what the solutions here might be. Or if there's, this other thing, I guess, just broadly is that if there are data sets that are not inside of OpenTopography, you'd like to see inside of OpenTopography, we always welcome people to say, hey, it'd be really helpful for my science if I could access this data through OpenTopo. And we can use that as motivation to go see what is involved in making that happen.
And next question is one we get a lot. Can the API access point clouds? Not currently. A lot of people would like that, and we're kind of thinking about whether or not we will implement that. We'd probably have to put on some controls because, as you know, point cloud files can get quite big, and so having people dynamically ask them through an API could get a little hairy. But it is something we are considering, so that might be available in the future. And
I will say that actually we have an API to access point clouds, but it's not publicly facing at the moment. But for certain partnerships that we have with other groups, we do provide that functionality, but it's sort of on a case by case basis. So this is another case of like if you're doing something that requires that type of access, you should reach out to us and we can talk about what we can provide. But we do have other partnerships with like other NSF funded entities, for example, that are harnessing OpenTopography as a backend where they can pull the data out and then do their own processing to produce other derivatives. So it exists, but it just isn't open to everybody, largely because, as Matt said, the computational demands of that API are quite significant. Yeah, pay to play for the point cloud API is maybe something, or again, just like for groups that have partnerships where we can forge a partnership that's mutually beneficial or is sort of within our core funding domain. So that would be National Science Foundation or other related activities. We should talk.
And just while it's quiet a little bit, I just want to put in a plug for, obviously these webinars are continuing next week. We'll be on 3D visualization of point clouds and topography using OpenTopography's Poetry Viewer and Cloud Compare. It'll be a different speaker, so you won't have to listen to me, but it's a really interesting topic and some really cool visualizations can be done with those two programs.
And then the other plug that I'll put out, and I for those of you that were there when we did the first webinar in the series, the kind of intro to OpenTopography, I put out a plug for this upcoming short course or workshop that we're running in Arizona in May. Matt, I don't know if you have quick ability to flip over to OpenTopography and go to that web page, but some of you have asked some questions that are sort of like what I would consider power user questions, things about building custom processing pipelines and things like that. And if you to learn, Matt, to learn and then workshops. Yeah, and then click that right there. So this workshop, applications are we're accepting applications for this. We have slots for about 50 people. And the application period closes at the end of the day on Sunday evening at basically midnight Mountain Time. But this will be a deeper hands-on, in-person only dive into some of the sort of tools that allow you to build potentially more sophisticated processing pipelines. They're similar to what you might get in OpenTopography, but are sort of this is designed around people wanting to do more advanced analysis of these kinds of data sets. So if you're interested in these topics, and you have the ability to come to Arizona, we will be providing some amount of travel support to offset the costs, things like lodging and things like that. So there's a link on that page to submit an application. So if you're interested, please do that before the end of the day on Sunday.
I think we don't have any questions. I guess we can wrap it up. Was there anything else, Chris, you wanted to mention, or?
No, just that again, this will get recorded and be online hopefully in the next 24-ish hours.
Thanks everyone for attending, and yeah, let us reach out if you have any questions that weren't answered here. Reach out to us and we'll get back to you.